Good morning. Myself, Kiran, working as an assistant professor in the Department of Mechanical Engineering, Global Academy of Technology, Bengaluru. So, in the previous lecture, we had discussed about the transformations, that is, translation and rotation were discussed along with the problems. And in the today's session, we'll discuss about the scaling and the homogeneous transformations and the concatenations along with few problems in depth. So what do we mean by scaling? As we know that scaling is either used to either to enlarge or to reduce the size of the element, and these scaling factors are used to alter the size of the object, and these scaling factors need not be equal in x and y directions. So in the first sketch we are seeing that the rectangle has been enlarged, and the scaling factor, that is Sx and the xy, that will remain same in both x and as well as the y directions. And in the second sketch we are seeing that the scaling factors Sx and xy are not equal in the x and y directions, and these points on the element can be scaled by the scaling matrix by using the following matrix equation, wherein x dash and y dash are nothing but the points obtained after performing the scaling, and Sx and xy are used to represent the scaling factors along the x and y directions, and xy is nothing but the original point, so that the p dash is equal to s into p. This is nothing but the equation which is used to represent the scaling. So let us try to solve one problem by using this scaling. So in this problem we have a rectangle with a length of 10 mm width, 10 mm length and 6 mm width, and it has one of its edge lying at the origin as it is shown in the figure. So here we need to determine the coordinates of the rectangle if it is translated by a distance of 3 units along x direction and 4 units along y direction. So here this rectangle is represented by the coordinates x1, x2, x3 and x4, and x1 is equal to 0, x2 is equal to 10, x3 is equal to 10 and x4 is equal to 0, and y1 is equal to 0, y2 is equal to 0, y3 is equal to 6 and y4 is equal to 6 here. And 3 and 4, as it is stated that it is translated by a distance of 3 units along x-axis and 4 units along y-axis here, which is given by the translational vector here. So p dash is nothing but the point obtained after performing the translation. P is, as you know, that p is given by this matrix and translation is given by this matrix. So adding the two matrices will give us the points that will give us a translated point, that is p dash is equal to p plus t. By performing this by adding these p plus t will give us the points after the translation. Next, similarly we can perform the scaling here. So in the second step it is scaled by a factor of 3. That means scaling factor remains same both along x and y direction, and the scaling factor is given by the equation 3 comma 0 and 0 and 3, and the position vector p is represented by the this particular matrix. So multiplying s into p will give us the points of obtained after performing the scaling. Similarly, in the third division it says that it is scaled by a factor of 2 units along x-axis and minus 1 units along y-axis. Means scaling factors remains different along x and y directions, which is given by this particular matrix. Again, multiplying the scaling matrix with the position vector will give us the point obtained after the scaling here. Next is the rotation. It is rotated, so in the fourth step it says that it is rotated by an angle of 45 degree with respect to the origin, that is theta is represented by the 45 degree, and rotational matrix is represented by cos theta minus sin theta and sin theta and cos theta, where theta is represented is given by 45 degree. Substituting 45 degree in the above equation will give us this particular result, and multiplying the rotation matrix with the position vector 0 with this position vector equation will give us this value p dash, that is equal to r into p, which is p dash is nothing but the points obtained after performing a rotation of 45 degree here. Next is rotation, rotate. Next, the element is tilted by an angle of minus 30 degree with respect to the origin. That means replace the value of theta by minus 30 degree in the above equation will yield us this particular value, and substituting and multiplying the rotation matrix with the position equation with the position matrix will give us the points obtained after performing a rotation of minus 30 degree. So this is how we perform the scaling, the rotation as well as the translation for the given problem. So next is said to be the homogeneous transformation. So what do we mean by this homogeneous? So homogeneous is nothing but either the matrix type, it should be either multiplicative or it should be additive type. But here in the case of transformation matrices for the rotation it is multiplicative type, whereas the matrix for the scale matrix for the translation is nothing but the additive type. So sometimes it becomes necessary so that we have to combine the transformation so that we have to achieve the required result. But in order to combine the transformation matrix, the matrix needs to be homogeneous. That is, it should be either multiplicative type or it should be additive type. So here the transformation matrices for the rotation and the scaling are multiplicative type, and the matrix for the translation is said to be the additive, so that we can convert the translational matrix into multiplication form by using this particular matrix. That means in order to obtain the homogeneity between all the transformation matrices, we have to convert either the matrices should be multiplicative or it should be additive. So here we are converting the additive type of the translational matrix into multiplicative type by using this particular matrix. So earlier, in order to represent the point, we used to represent this particular equation. So instead of using this particular equation, I can use this matrix. So in order to convert the additive matrix into multiplicative type. Similarly, the translation matrix for a line, it was represented by dx and dy in 2 cross 2 dx comma dy. The same translational matrix can be converted into multiplicative type by using this particular matrix here. So earlier, in order to perform the translation, we used to add the translational vector with the positional vector, but here instead of that we can multiply this translational vector with the positional vector so that we can obtain the points after the translation here. So similar kinds of the changes can be obtained for the line, rectangle as well as for the rotational matrices here. So we'll try to know what do we mean by the concatenation in the next slide. So here the concatenation of the transformation means we have sometimes it becomes very necessary that we have to combine the scaling, the rotation as well as the translation. So in order to combine the transformation matrix, so that combination of these matrices, that is scaling, rotation as well as the translation, so that particular process we call it as concatenation, which is nothing but the combining the transformation so that we can obtain a single transformation matrix. And these combined transformations are called as concatenated transformation, and the main objective of this concatenation is to accomplish a series of transformations so that we can obtain single transformation. That means I have to obtain a single transformation matrix by combining these the three different matrices such as scaling, rotation as well as the translation. So here let us try to illustrate this concatenation by using an example. So here I am trying to rotate an element about an arbitrary point here. So in this case the sequence of transformation would be I need to perform the translation first, then I have to perform the rotation, then I need to translate it back to the original location. So rather than this, if we can perform the concatenation here, that is in this case I can magnify the element. That means I can perform the scaling here. So in this case magnifying the element but maintaining the location of one of the points in the same location. So in this case the sequence of transformation would be the scaling, then translate it back to the desired point. So let us try to illustrate this concatenation by using a simple problem. So here we are trying to determine the position of a point, that is 3 comma 1, after scaling by a factor of 2, then rotated by a factor of 45 degree. So initially we'll perform a scaling factor that remains same, that is scaling factor is given as 2, which remains same both along the x and y directions. So multiplying the scaling matrix with the position vector will give us the points after the scaling, and this scaled point can be rotated by an angle of 45 degree along both along x and y axis, which is given by rotation. That means we need to multiply the rotation matrix with this matrix x dash comma y dash, so that we can obtain the point after the translation, after the rotation. That is, multiplying rotation matrix with the position vector will give us this particular value. That means initially I have to perform scaling, then I need to rotate so that I can obtain the position of the point. But in the concatenation I can combine the scaling as well as the rotation, so that I can obtain a single transformation matrix. That is the same result. That means what this value which that is 2.828 and 5.657 can also be obtained by performing this concatenation. That means here initially I have done the scaling, then I have performed the rotation. So in the next step I'll combine scaling and rotation so that we can illustrate the concatenation here. That is, the same result can be obtained by concatenating the two separate transformation matrices. That is, I am performing the scaling and the rotation in the same matrix. That is, S into or scaling matrix into rotational matrix will give us this particular value. Now applying this concatenated transformation matrix to the original point x comma y. That means I have combined the scaling as well as the rotation, then multiplying that with the rotation matrix with the position vector 3 comma 1 will give us the same value as we obtained it earlier, 2.828 and 5.657. This was the same values which we obtained once we did the scaling, then we perform the translation, then we perform the rotation here. So this is what we do called as a concatenation. Thank you.